In this presentation, I am going to explain the previous GATE questions and answers, and the topic covered is power electronics. Now let us see a GATE question that is in 2013 and that carries 2 marks. The thyristor T in the figure below is initially off and is triggered with a single pulse of width of 10 milliseconds. It is given that the value of the inductor equal to 100 divided by pi, that much microhenry, and the value of the capacitor equal to 100 divided by pi, that is equal to microfarad. Assuming the latching and holding currents of the thyristors are both 0 and the initial charge of the capacitor is 0, T conducts for what is the duration of the conduction of this thyristor? That's the question. Options A 10 microsecond, B 50 microsecond, C 100 microsecond, and D 200 microsecond. Now, as the thyristor conducts, you know that the equivalent circuit will be like this one. Once the thyristor is conducting, this is the equivalent circuit in which a DC voltage source of 15 volt is applied, and the value of this the inductor and C capacitor is given. This is a simple LC circuit. Now we have to derive the equation for the current, and for that one, we have to write the corresponding equation, that is L di by dt plus 1 by C integral I dt equal to the input source voltage Vs. That is, as in this problem, it is 15 volts. Now, we have to derive the equation for this current flowing through this LC circuit. Once the thyristor is on, you have to take the Laplace transform of this equation, or the L into SIS minus initial value of the current plus 1 by C integral Is divided by S plus initial charge of the capacitor Q0 divided by S, that is equal to the source Vs by S. Therefore, this is the Laplace equation for this, circuit. And from this one, we have to find out the equation for Is, that is Laplace transform of the current flowing through this one, and that is derived from this one, substituting the I0 as well as Q0 equal to 0. We are rearranging this one, and you can derive the equation for current, Laplace transform of the current, which is equal to Vs divided by L into 1 by S square plus 1 by LC. From this one, you can find out the inverse Laplace transform of the current, that is Is, that is in time domain we can find out, which is equal to Vs divided by root L by C. Root L by C is called the characteristic impedance. The input voltage Vs divided by root L by C sin omega naught t, where omega naught is called the resonant frequency, which is equal to 1 by root of LC. Therefore, this is the current waveform, this is sinusoidal current waveform, and this is the duration for which the current is flowing through this LC circuit or through this LC circuit. Therefore, this duration, once at this point the current reduces to 0 and the device gets turned off. The question is that what is this duration for which this thyristor is conducting? The equation for this duration is given by pi by omega naught. Pi by omega naught, where omega naught is called the resonant frequency, which is equal to 1 by root of LC. Now, continuing the same problem here, this duration we have to find out, that is the duration for which the thyristor is conducting. This is equal to pi by omega naught. For that, first we have to find out what is the characteristics resonant frequency, that is omega naught you have to find out. That's omega naught is given by 1 by root of LC. Omega naught equal to L value is given 100 by pi microhenry, C value 100 by pi microfarad. Substituting that one, we'll be getting it is equal to 10 to the power of 4 into pi, that is omega naught, and the conduction period is given by pi divided by omega naught, or pi divided by omega naught means pi divided by 10 raised to 4 into pi, or that's equal to 100 microseconds. This is equal to 100 microseconds. Therefore, the answer is option C. This duration is equal to for which the thyristor is conducting, that is given by 100 microsecond. Now let us see another problem, 2013 GATE question, and that carries 2 marks. The separately excited DC motor in the figure below has a rated armature current of 20 amperes and the rated armature voltage of 150 volt. An ideal chopper switching at 5 kHz is used to control the armature voltage. This is the chopper circuit that is used to control the armature voltage. If the value of the armature inductance equal to 0.1 millihenry and armature resistance equal to 1 ohm, neglecting the armature reaction, the duty ratio of the chopper to obtain 50% of the rated torque at the rated speed and the rated field current is what is the duty ratio of the chopper to get the 50% of the rated torque at the rated speed and rated field? That is the question. Now the options are A, it is equal to duty ratio equal to 0.4, B 0.5, C 0.6 and D equal to 0.7. That is the duty ratio. Now let us see the rated armature current that is given as 20 amperes. That is rated armature current of this motor is 20 amperes. This is specifically told that it is a separately excited motor, and the rated armature voltage, that is the armature current equal to 20 amperes and rated armature voltage is equal to 150 volt, and the value of the inductor is given 0.1 millihenry and armature resistance equal to 1 ohm, and the basic relation of the torque and flux and armature current is equal to torque is proportional to phi into Ia. For a DC machine, torque is proportional to phi into Ia, but since it is a separately excited motor, the flux can be assumed as a constant, it's not changing as such, or torque can be proportional to the Ia. The torque produced by the motor is proportional to the armature current. Now the back EMF, the relation of the back EMF and applied armature voltage and the armature resistance drop is given by V equal to EP plus IARA, or the back EMF equal to the voltage at the armature V minus Ia, the rated value of current, 20 amperes rated, Ia into Ra. One thing is that we are not considering the inductance, it's because the average value of the voltage of the across the inductor or one switching period, that will be 0. That is why that drop is not considered here. That is why here V minus IARA, that is 150 minus 20 into 1 ohm, that is 130 volt is the back EMF corresponding to the rated current and the rated voltage. Now at 50% of the rated torque, 50% of rated torque means that since T is proportional to Ia, the Ia will be 50% of the rated value, or Ia will become now 10 amperes. And since the speed, we have said that is the rated speed is the rated and the flux is at the rated value, the back EMF is not changing because E equal to 5 ZN divided by 60 into P by A. N is not changing, it's a rated value. Similarly, the flux is also at the rated value. That is why the back EMF is not changing. In the second case, the same back EMF. Therefore, the required armature voltage in the second case, that is when 50% of the torque condition, E equal to, or the required armature voltage can be calculated as back EMF plus IARA. Back EMF already we calculated, it is equal to 130 volt. Therefore 130 plus IARA. Now current has been reduced from 20 amperes to 10 amperes. Therefore 10 into the armature resistance equal to 1 ohm. Therefore it is equal to 140 volt. Therefore the required armature voltage in the second condition where the torque is 50% of the rated value, that is equal to 140 volt. Now in order to get 140 volt from the 200 volt with a chopper, the required voltage of the armature equal to 140 and the input voltage equal to 200. Therefore the input voltage of the chopper is equal to 200 volts. The duty ratio is given by the output voltage, that is 140 divided by the input voltage 200, which is equal to 0.7. Therefore the duty ratio is equal to 0.7. The answer is option D. Option D is the answer. Now let us see another question, 2013 GATE question that also carry 2 marks. And this is common to the data is common for this question as well as next question, question 3 and 4. And the figure shown below, the chopper feeds a resistive load from the battery source. From a battery source, this is a chopper. Actually, it is called a boost converter. Like it is a step-up chopper, and this is a source. This is a source. Of course, this is a load, resisting load, and battery source. MOSFET Q is switched at a frequency of 250 kilohertz. The frequency of this MOSFET switching is equal to 250 kilohertz with a duty ratio 0.4. That is on period divided by the total time period. That's called the duty ratio 0.4. All the elements of the circuits are assumed to be ideal. The question is that the peak-to-peak source current ripple in amperes. The current through the source current means the same as the current through the inductor. What is the peak-to-peak value of that one? Therefore, let us analyze the circuit, and before that one, the options are option A 0.96, option B 0.144, option C 0.192 ampere, and option D 0.228 amperes. Therefore, as a solution of this one, first this is a step up chopper as such, and the input voltage equal to 12 volts, and this is the input side inductor value is given. That value is given as 100 microhenry, and the source voltage is given as 12 volts, and this is the MOSFET that is triggered at a 250 kilohertz, and the diode and capacitor value as well as the resistance values are given. Now when the switch is on, the MOSFET is on, this inductor is directly coming across the source. Therefore here the equation is, now if you write the KVL equation for this one, which is equal to, that is Vs equal to, or this voltage equal to Vs equal to L di by dt, or we can say that one, the source voltage Vs divided by L, that is equal to the rate of change of current through the inductor. Vs equal to 12 volt and inductor equal to 100 into 10 raised to, it is equal to 100, it is given as 100 microhenry for 100 into 10 raised to minus 6, and that is equal to the rate of change of current through the inductor, because L di by dt equal to this voltage, input voltage. Therefore that's why VL by L equal to 12 divided by 100 into 10 raised to minus 6, that is equal to DIL by dt, rate of change of current through the inductor, which is same as the rate of change of current means, and the switch is on, the current is building up and linearly it is increasing, and once the switch is off, the current is dropping off. This is the duration for which the switch is on, and this is the peak to peak current, means that from here to here, what is the peak to peak current? Therefore that change in current is equal to IL peak to peak divided by this period is called on period. Therefore IL peak to peak divided by the on period is the rate of change of current through the inductor, which is same as the rate of change of current through the source. Therefore the peak to peak source current is same as the peak to peak inductor current. Therefore that is equal to IS peak to peak. IL peak to peak is already calculated as, which from this one, VD divided by L into T on, into the on period. Therefore the question is that you have to find out what is this peak to peak value of the inductor current, which is same as peak to peak value of the current, the source current, because inductor is in series to the source. And in order to find out VD value is given, L value is given, you have to find out what is the T on, and you have to substitute in this equation. T on can be found out by duty ratio is given as 0.4 and the frequency is given as 250, and duty ratio is given by on period divided by total time period. Therefore the total time period is given by 1 by 250 into 10 raised to 3, which is, this is the total time period TS, and the duty ratio equal to is given as 0.4. Therefore it is equal to the duty ratio is equal to, from this equation we can calculate what is the only the unknown is T on is given, T on is to be calculated, duty ratio is given, then you can calculate what is T on, which is equal to 1.6 microseconds. That is the on period of this one, this duration is the on period of that one, that is equal to 0.4 duty ratio into TS, 0.4 into TS, TS already calculated 1 by 250 into 10 raised to, it is kilogram into 10 raised to 3, or substituting that one, we'll be getting 1.6 microsecond is the on period. Once you get the on period, you can calculate this peak to peak current through the inductor or through the source, which is equal to Vs divided by L into T on. It is equal to Vs or the VD or the input voltage VD divided by L into T on, and which is equal to 12 divided by 100 into 10 raised to minus 6 into the on period, 1.6 into 10 raised to minus 6, or from this one we'll be getting, it is equal to 0.192 ampere. The peak to peak current through the inductor, which is same as the peak to peak current through the source, that is equal to 0.192 ampere. Therefore, the answer is option C. 2013 gate question. It is the data is same as the previous question and the same. This is a boost converter or step up chopper in which the input voltage is equal to 12 volts, and the question is that the average source current in ampere in steady state. What is the source current average value? Therefore, when switch is on, we have seen that the current through the inductor is building up like this one, and this is the IL peak to peak. This difference in that is IL peak to peak. And once the switch is off, the circuit is like this one, the path is like this one. In that case, here the voltage across the inductor will become the difference of this output voltage, input voltage minus output voltage, or negative voltage comes here. That is why the current is di by dt is negative. So current is dropping like this one with a negative slope until the off period. For that will be continuing. Therefore, this is the current at the input side. This is during the on period, and this is the current through the inductor during the off period. The question is that what is the average value of this source current or the average value of the inductor current, because inductor current is same as the source current. The question is that average value of the source current means that average value of the inductor current. Now to find out the average value of the inductor current or source current here, now let us see the average output voltage is given by duty ratio is given as 0.4. Input voltage is given as 12 volts. The output voltage and input voltage are related in a boost converter or say boost chopper as such. It is equal to V0 divided by Vd equal to or 1 by 1 minus d. Or the output voltage is given by 1 by 1 minus d times the input voltage. Therefore 1 minus 0.4 into 12 volt or 20 volt is the average output voltage. Once you get the average output voltage, average output current can be calculated by dividing the resistance. Therefore, average output current equal to 20 divided by 20 ohm or 1 ampere is the average output current. Now again, by using the same duty ratio here, the average input current can be calculated because average output current divided by average input current, source current is given by 1 minus d. That's the equation for a boost converter. Therefore, from this equation, average source current or input current can be calculated as average output current divided by 1 minus d, or 1 ampere is the average output current divided by 1 minus duty ratio 0.4, or which is equal to 1 by 1 minus 0.4, which is equal to 5 by 3. Therefore, the average source current or average current through the inductor, which is equal to 5 by 3. Therefore, the answer is option B. And now let us see another question, 2013 gate question that carries 1 mark. Statement for link the answer question, this one, 5th and 6th, for this question and the coming question. The same statement can be used. And the voltage source inverter shown in the figure, that is this one, what shown in the figure, is switched to provide 50 Hz square wave AC output voltage. Therefore, this is the same circuit in which this is giving a 50 Hz square wave output, and the across the RL load. Therefore, the load is RL load. Across this one, we are getting a square wave, the voltage VSI, voltage source inverter. And the reference polarity of V0 and the direction of the output current are indicated in the figure. Here, it is indicated that this is plus and this is minus. Similarly, this is the positive current. Therefore, this is the positive direction of the current. And the positive voltage means here plus and here minus. That is the polarity of the output voltage, and the currents are given in the figure. It is given that resistance R equal to 3 ohm and inductor equal to 9.55 millihenry. That is given. And the question is that in the interval when the output voltage is less than 0 or negative and the current output current is more than 0, it is positive, the pair of the device which conducts the load current is out of this one, here S1, here D1, S2, D2, S3, D3, S4 and D4. Therefore, these are the switches S1, S2, S3, S4, and these are the feedback diodes like D1, D2, D3, D4 are the feedback diodes. Therefore, the question is that under this condition, when the output voltage is negative as well as the output current is positive, means that here output voltage is negative, means that output voltage is here, positive means here and plus and here minus. But it is since negative means here it becomes plus and here it becomes minus. Second one, I0 is more than 0. I0 more than 0 means that it is positive. Therefore, I0 is in this direction. Now, out of this one, which all the devices are conducting under this condition? The options are A, Q1 and Q2. These are the Q1 or Q1. I have written it is equal to Q1, Q2 rather than I am written S1 and S2. Same thing. You take it here also. Q1 and Q2. And next one Q3 and Q4. Same circuit here. Q3 and Q4. C is D1 and D2. Here D1 and D2. The option is D3 and D4. D3 and D4. Same circuit I marked. Instead of Q, I mark it as S also. Therefore, in this case, we can see that one. This is the voltage and this is an RL load. Here, the current is of this shape. It is there. This is the shape of the current. And the question is that when the voltage is negative as well as current is positive. Therefore, this is a duration. This is a duration which voltage is negative less than 0 and current is more than 0. In that case, voltage is negative means here plus and here minus. Current is positive means in this direction. Therefore, since the current is in this direction and here plus and here minus, this is to be connected. This is the negative terminal and this is the positive terminal. Plus and minus is a positive. Plus and minus a positive, or this is a positive terminal. When it is negative voltage means this will become plus and this will become minus. Then only voltage will be negative. Therefore, this is plus means this diode has to conduct because the current is in this direction. Therefore, the current is in this direction means then we'll be getting a positive polarity here. Similarly, the diode, the current in this direction means here also we will be getting a negative polarity, means the voltage polarity is now reversed. Here negative and here plus. But the current direction is same as the previously. Therefore, the devices that are conducting is given by these two. D3 and D4 are the devices that are conducting during this duration when output voltage is negative and the output current is positive. That is this duration. This duration, of course, D3 and D4 are conducting. D3 and D4 are conducting. The answer is option D. Now let us see another problem. 2013 gate question that carries 1 mark. The data is same as the previous question. And the appropriate transition, that is zero voltage switching ZVS or zero current switching of the IGBT during the turn on or turn off is, option is ZVS during turn off, option B ZVS during turn on, option C zero current switching ZCS during turn off, and D zero current switching during turn on. Therefore, in this case, if you are looking into this one and if you look into here, that is when, for example, when you are switching on, just before switching on of this one, that is when getting turned on, that is Q3 and Q4 are just turned on. Just for instance here, we can see that from here Q3 and Q4 are getting turned on. And just before that one, the devices that are conducting is equal to D3 and D4. Since D3 and D4 are conducting, just before turning on these two things, that is Q3 and Q4 or S3 or S4, since the diodes are conducting, the voltage drop, that is, since the diodes are conducting, the voltage drop is very negligibly small, almost zero, the voltage drop. That is why it is getting turned on when the devices Q3 and Q4 are getting turned on. Because of the drop in the diodes are zero, almost zero, only diode comes. That is why it is called zero voltage switching comes. For ZVS comes here. Therefore, that is why when Q3 and Q4 are switched on, initially due to in the reverse current, it remains off state and current passes through the diode. In this condition, the voltage across Q3 and Q4 are zero as the diode conducts. Hence, it shows zero voltage switching ZVS during the turn on. During the turn of these switches, just before that one, since the corresponding diodes are conducting, that drop is very less. That is why these switches are becomes zero voltage switching ZVS during the turn on period. Therefore, the answer is option ZVS during the turn on period, or the answer is option B.